Okay, the simplest, most definition of an acid is a compound, a chemical compound that will disassociate a hydrogen ion. That's the most simple definition. Now it's got to be an ion. It cannot be either an H minus or an H atom. It's got to be H plus. Now disassociate means coming apart. The opposite of a base, the opposite of an acid is a base. And the base, same basic definition, the idea that an hydroxide ion, OH minus, will disassociate. So just because it has an OH, if it doesn't disassociate, then it's not a base. Okay. Again, it's crucial. It's got to come off. It's got to disassociate. Otherwise, it's not a base or it's not an acid. Now, within that context, we have three situations. We can have a strong acid. That's where 100% of the hydrogen ion comes off. Now, some people refer to H plus as a proton because the hydrogen atom has one electron and one proton. So when the electron's gone, the only thing left is the proton. So a lot of books, a lot of people will say, this is a proton disassociating, and it is. And there's some other definitions of what an acid is. There's probably 3 or 4 of them. Now we get to the acid-base chapters, we'll talk in detail about the differences between all those. Okay, so we can have a strong acid. What else do you think we can have?
Weak acid.
A weak acid, right? What do you think a weak acid would be if a strong acid comes off 100%? Comes off less than 100%. 50, even 1%, still an acid. And there are 7 strong acids, okay? Hydrochloric, nitric, these are the most common of the 7. There are others that are significantly less common. These you run across all the time. This is the acid you have in your stomach, hydrochloric acid. It's also called muriatic acid, which is an old term for it. Nitric acid is called printer's acid. Sulfuric acid is pretty common too. Now, when you take OChem, you'll be using frequently concentrated sulfuric acid. This is a really badass acid when it's concentrated. It will dissolve flesh quite easily. But you use it frequently in OChem. And the higher you go in chemistry, the more potentially higher risk chemicals you're using. And in organic chemistry, you frequently use really hard oxidizing agents, concentrated acids, concentrated bases, which we'll talk about in a minute, just to get the acid, reactions moving along. But these are the 3 most common ones. And you really should know both the formula and the name, the modern name. Now, the thing about acids, both weak and strong, is sometimes they have multiple protons that can come off. So hydrochloric acid has one proton that can dissociate. Nitric has one. Sulfuric, however, has two protons that can dissociate. One comes off significantly easier than the other one. If one proton comes off, it's called a monoprotic acid. Two come off, it's called a diprotic acid. Phosphoric acid is a triprotic acid. Citrus acid is a triprotic. There's a number of, it doesn't go past 3. There's some rare ones, but it doesn't go past 3. And the 3 aren't that common either.
Is that third acid really, really strong?
No, no. And the first one comes off easiest, the last one comes off the hardest. So exactly right. So it would go hardest, middle, weakest coming off. Good question. Okay. Now I want you to pay attention to those arrows. Notice there's one arrow. And a while back, we talked about reactions, I said there's always 2 arrows. Okay. If we're talking about a strong acid, it's 1 arrow. That means everything goes over to the dissociated state. That means there is none of this around. It's all been taken apart. Okay, in the case of a weak acid, there are millions of weak acids. You have to memorize those by next week. No, okay, so an example of a weak acid would be vinegar. Now that's one way of writing vinegar. The other way would be to write it like that. I prefer this one. This is one of the more simple organic acids. And this is what makes it an organic acid, the COOH. And then there's a group over here. It could be an H, it could be 1 carbon, it could be 18 carbons like a fatty acid. The part that makes it an acid is this on the end. Notice this has 2 kinds of H's. What makes it an acid is this H, not these H's. These don't come off, period. This one comes off easily, hence it's an acid. Now, that is a weak acid because less than 100% dissociate. Frequently, significantly less than 100%. So that means whenever we draw a reaction, yeah.
Both of these equations of vinegar, you have 6 hydrogen on one side and 4 on the other.
Oh. What do you mean? Yes. I could say because I'm a dumb shit, but I didn't say that. All right, so this is called acetic acid. And this is the same stuff called vinegar. Vinegar is 5% acetic acid, 95% water. If you buy vinegar at the store, it will be 5% by law. Otherwise, they cannot call it vinegar. So when they make it, if it's less than 5, they bring it up They fortify it up to 5. If it's more than that, they dilute it down to 5. Now you can make your own vinegar. Just buy 100-year-old wine. This $1 million wine, investments and all this stuff, the wine is awful most of the time. So what happens during yeast growth, yeast make alcohol, ethanol, till they poison themselves when they make too much alcohol and the yeast all die. However, they can continue to do that under certain conditions and ends up making vinegar. And really awful wine kind of tastes like balsamic vinegar. Okay, so what does now notice I have one arrow there. Now, whenever we do weak acids, I want you to draw your arrows like that. Okay, 2 arrows. Number 1, the smaller one is the one going forward. The bigger one is the one over here. That means there's more of this than this. And depending on how weak or strong the weak acid is, these arrows are going to be varied. But whenever you do a weak acid, though, it's always good to indicate that it's weak acid by doing 2 arrows, strong acid by 1 arrow. Okay, and notice I put the acid part at the end rather than the beginning. Frequently it's that way. Sometimes it's not, depending on your textbook philosophy and that. But there's a whole bunch of weak acids. I mean, when you get into biochemistry in particular, you'll see a whole bunch. Citric acid, salicylic acid, I mean, there's just a zillion of them. Nature likes weak acids. Okay, and the last category is going to be a non-acid. And let's take something, we're talking about wine, let's talk about an example of a compound. Ethanol. Ethanol is drinking alcohol. Now, the reason why, remember what drives reactions all the time? What have I always told you? Stability. With the strong acids, that means what it's disassociating to is stable, more stable than what it's originating. Weak acids, this is sort of stable compared to this, but not, differences are very little. So this ends up being more stable than that. With non-acids, this is horrendously unstable. This is called a carboanion, very unstable. So if the H doesn't dissociate, it's not an acid. So in organic chemistry and biochemistry, there's a ton of non-acids. A lot of carbons, hydrogens, and oxygens in our body, but not all of them dissociate. Okay, on the other side of the spectrum, is like what? Yeah, neutral in terms of non-acidic, non-basic, yes. All right, so the opposite of a base is, the opposite of an acid is a base. Sometimes people call it alkaline. Alkaline is an old term from quite a few hundred years ago, but it's still around a lot. You have alkaline water. Who's heard of alkaline water? What's the oxymoron with alkaline water?
Water is very slightly acidic.
Depends on your local water agency out of the tap. It should not be slightly acidic. That's the problem with Flint, Michigan, is it was acidic. It's usually slightly alkaline,
Oh,
slightly on the basic side of neutrality.
not oxymoronic.
Hmm?
So it's redundant, not oxymoronic. You mentioned alkaline water was a popular.
Oh, yes. So what do you think alkaline water is?
Water.
Good. And what's our topic we're talking about here? Huh? Yes. They claim that's very healthy. Guess what's in your stomach? Acid. So guess what acids and bases do?
Water and salt.
They make water and salt, and they neutralize one another. So it's absolutely a waste of money to buy alkaline water because it's totally neutralized as soon as it hits your stomach. So from here to about here, it's alkaline. Then as soon as it hits here, you just wasted your money. And there's an acid and alkaline diet. That refers to amino acids have three parts. They have an amino and NH2 group. They have an acidic group, and they also have a side chain. And the side chains can either be neutral, acidic, or basic. So what they're doing is they're looking at a protein and looking at the side chains and balancing those out, whether they're more acids than bases, more bases than acids, or more neutral. And that's whether it's acidic or alkaline diet. Yeah. A free radical is neither an acid or base. That's when an electron leaves an atom and then leaves a electron unpaired. And an electron's unpaired is extremely unstable. So a free radical wants to become stable, right? So it immediately grabs the closest thing to it to become stable, which sometimes is not good because it's not supposed to be doing it according to our pathway, biochemical pathways in our system. So free radical is different than these. That's when an electron comes off rather than a proton. And again, they're awfully unstable. I mean, same with the carbocations. We're going to see in a minute carbo anions. Those are also unstable. Okay. So alkaline water, not good. Okay. Now, everyone always thinks of what's the opposite of an acid? The base. The reason why it's opposite, I'm going to show you in a minute here. First, let's define a base. Okay. So that's the tendency again for a compound to disassociate a hydroxyl ion, an OH minus. Just like with acids, it's an H plus. In this case, it's an OH minus. Okay, so we have strong bases. The two I want you to know are sodium hydroxide, potassium hydroxide. These are considered, sodium hydroxide is called lye, and frequently lye has a whole bunch of potassium hydroxide in it. Now, if you want to make soap, what you do is you combine fat plus a strong alkaline or strong base. That's called lye soap, or ivory soap. That's lye soap. And these are strong bases. That means the OH comes off 100%. One arrow. Oops. Okay, so there's sodium, potassium hydroxide, strong bases. And then like acids, we have weak bases, which means we disassociate less than 100%. and that's ammonium hydroxide. Ammonium hydroxide, if you go to the store and buy ammonia, well, the way they make ammonia is they take NH3 gas, ammonia gas, and dissolve it in water, and it becomes ammonium hydroxide. So this is really what you're buying at the store. You're not buying NH3. You're buying NH3 in water, which becomes ammonium hydroxide. Now, there are two kinds of cleaning products. One is good for grease. One is good for cleaning off water spots. You need something to clean off water spots that's acidic. And to clean grease, you need something that's alkaline. So you use ammonium hydroxide to clean your stove after you fry something, all the splatters. On your windshield in your car or your glass at home, you want to spray with something that's not has ammonia in it. The water spots are just dried minerals, and the acid will put them into solution. Now they have a lot of these combination cleaners that have a little of each. It's better to focus on one cleaning process instead of getting combination. So grease, you want ammonium hydroxide. Water spots or mineral spots, you want something like Windex. Doesn't have any ammonia in it at all. Okay, so those are weak bases. Then of course we have non-bases. And that's going to be like, let's just use ethanol again. So in organic chemistry, frequently, a lot of ways of looking at reactions are how stable is what you're starting with, the reactant, how stable is the product? And that will determine how much the reaction will happen. And there's various ways to determine that. We're going to be getting into something called equilibrium. And equilibrium is a ratio of product to reactants. So the bigger the equilibrium value, the more product you have. So the more stable the product is compared to the reactant. Again, it's a stability argument. Okay, now, in between an acid and a base, when we put an acid and a base together, yeah.
Explain a little bit more of like the non-acid, non-bases, just that like makes reactions really unstable.
The product is unstable.
Or, yeah, sorry, the part is unstable.
Yeah,
So
that's why it doesn't want to happen.
Okay, so do they usually happen or do they have to be like forced out?
You have to force it big time. And frequently in organic chemistry, you'll find those as intermediate products that immediately react because they're so unstable.
Okay.
It's totally a stability argument.
Okay.
So you have to look at what you're trying to make and what you're making it from. Remember the reaction did in lab with the thing that's cool with all the fire and everything? Okay, that was an oxidation reduction reaction, which means electrons are being transferred. But the product is so much more stable than what they started with. It happens really fast. So again, it's stability of what you're making versus what you're coming from. Does that make sense? Okay, when we mix an acid and a base, now remember an acid has to dissociate a hydrogen ion, proton, and a base has to dissociate a hydroxyl anion. However, we mix those two together, guess what we make? H2O. So when we mix an acid and a base together, like hydrochloric acid and sodium hydroxide, we end up with H2O plus sodium chloride. So this reaction is so incredibly stable that this is big time driving force. So when you mix acid and base together, it's very frequent that you'll get a very hot reaction. Energy is being given off. When energy is being given off, that means your product is very stable because it's taking that potential energy that was stored in the bonds of your reactants and converting it to energy that leaves the system. And that's what you're feeling when the reaction happens, or you're measuring with the thermometer, because the thermometer is going to measure the kinetic energy or the motion of molecules. Motion increases, temperature goes up. So Celsius is a metric used for that. So is Fahrenheit. Okay. Now, this is what our lab's about. We're gonna take an acid and a base, and we're gonna mix them. What's gonna happen? It's gonna form water. Now, if we have 1 mole of hydrogen ions, 1 mole of hydroxyl ions, how many moles of water are we gonna get? One, because this is balanced the way it's written. 1, 1, 1. Okay, so oops. Okay, so if we have 1 mole of hydrogen ions, 1 mole of hydroxyl ions, we get 1 mole of water. What if we have 2 moles of H plus and 1 mole of OH? What do we get now? One what? Of what? Water. So we end up with excess hydrogen ions because these are related 1 to 1. So for each mole of that, we're going to use 1 mole of this. We have 1 mole left over. So when we have a lopsided acid and base reaction, then we end up with excess acid. Hence, your reaction is going to be acidic, the product. And likewise, if we have excess base, we're going to end up with 1 mole of water again and excess hydroxyl ion. Now, this is the essence of titration. This is what we're going to be doing today, tomorrow, Thursday, and Monday. Lots of titration. And the idea here is if we can add a little bit of this, a little bit of that together, so we end up with this neutral solution, we can figure out how much of the other one was used to get it. So there is a metric, it's called pH, and that's used as a measurement of how much H you have and how much OH is present. Now, the definition of the P part of the pH is the negative logarithm of the hydrogen ion concentration. How's that for a mouthful? You know, pH, POH, P sugar, there's a whole bunch of P's used in biochemistry. So when we get to acids and bases section, we're going to talk a lot about pH. But for right now, and probably a lot of you have heard of pH, and it's just a measurement of, in this case, acidity. But the thing is, it's a negative logarithm, another fancy word for an exponent, the logarithm. So because it's a negative exponent, when the pH is low, that means it's strong acid. When the pH is high, that means it's a strong base or extremely weak acid. Okay, so at pH 7, that's when there's no I'm going to say no here as a qualified no, because there's a tiny bit of H plus present and a tiny bit of OH minus. But for our purposes right now, we're going to say no. But I'm going to refine that big time. It's called autoionization of water. We'll get to when we study the chapter on acids and bases. Okay, so when we're at pH 7, that's considered neutral. That means it's neither acidic nor basic, pH 7. Now going back to Flint, Michigan again, their water was acidic. It was a pH 5 something. That means it's on the acidic side. Acids dissolve metals. Well, in Cleveland and all those older cities, they had a lot of lead pipe. And lead can be dissolved, lead metal can be dissolved with acids, creating the lead cation. Heavy metals bond really strongly to proteins, specifically the cysteine amino acid of a protein. If that protein is involved as an enzyme, that enzyme will stop functioning. So if you get a lot of lead in your system, a lot of your enzymes get all messed up. Hence the neurological damage, there's a whole bunch of stuff going on. So heavy metals are really bad. Up until about middle 70s, they still used something called a lead gooseneck in building. Because what happens is, I had a good friend of mine had an older house in Tacoma, and he had this problem, and he didn't know what a gooseneck was. Okay, a big pipe comes from the street to your house, and your house has a mating for it. They're never 90 degrees. They're always off. So what they do is they put a lead gooseneck there, and lead is soft. You can actually move it. So what they do is they move it so that the angle of the pipe coming from the street to the house is perfect. It's also lead. So even though you have no lead in your system, you have a little bit of lead in that gooseneck. They stopped doing that, by the way. And if your water is slightly acidic, like Tacoma's water's about 6.3, something like that, then you're going to be leaching away not only lead, but also iron. A lot of iron pipes are used. Galvanized is zinc coated. You get zinc in your water, you get iron in your water, and sometimes lead. Very bad. Okay, so the goal is neutrality, pH 7. Okay, so that means these have to be balanced from a mole perspective. Equal base, equal H plus against an equal base, equal OH, 1 to 1. Now, when we do a titration, we can use a meter, a pH meter, and it'll tell us we're at 7 now. But usually pH meters are expensive and they usually don't have them in labs. They have something called an indicator. So an indicator will tell us pH. An indicator, we all use pH paper, remember? In lab, that orange paper. That orange paper has a whole bunch of indicators dissolved on it. There are like 6 or 7 of them. And depends on the color will determine the pH. Now, for acids and bases, we want an indicator that tells us we're at pH 7. Now, the indicator we're going to be using lab, the long name, phenolphthalein. Phenolphthalein is an indicator that when it goes from colorless to pink, we're at pH 7. Okay, so what we do is we start with an unknown acid in a beaker. And the goal is to determine the concentration of the acid in the beaker. And what we do is we're using a burette. The burette contains some kind of a base. And then we drop the base into the acid until it's exactly neutralized. So we put about 3 drops of phenolphthalein in there. We go drop, 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 drop. And this goes from colorless to Barbie pink. It's a great color. Then we know we've reached neutrality. Now the trick is you don't want to be pretty Barbie pink. You want it to be barely, barely, barely pink for a true endpoint. And that's what you're going to practice today. Now, you need to know a little bit more about solution concentrations to figure out your concentration. Okay, so what we need to do is okay, so solution concentration. Now, solution concentration is given as moles per liter. And the official is moles of solute per liter solution. But for now, for this series of labs, all we need to know is moles per liter. Now, remember on the last lab, you had the 3M stuff and the 1M stuff. This is what they're referring to. So the 3M stuff is 3 moles of acid per 1 liter of solution. The 1 molar stuff will be 1 mole per 1 liter. That's what that means. And they usually represent that with a uppercase M slant or italicized. So 3 molar acid is going to be 3 moles (1 liter) solution. Now, when we have 3 molar, how do you know how many moles of acid are really in there? What if you have a half a liter? How many moles of acid are in 3 molar acid? 3 molar acid and you have a half a liter,
Oh,
how many moles of acid do you have?
1.5.
How did you get that?
I took 1/2 liter times 3 times 3.
Yeah, exactly. Okay, this is a dimensional analysis problem. Okay, so we have so you start with liters, and what do we multiply liters by to get moles? A conversion factor, right, with moles and liters in it, which happens to be concentration. Liters cancel gives us 1.5 moles of acid. Okay, what that means is we're taking volume times molarity equals moles. That's the key here. Volume in liters times concentration in liters gives us moles. Volume in milliliters times molarity in milliliter, moles per milliliter will give us moles also. But normally it's in liters. That's the standard. So VM, I'm using that for the next 4 days. VM, volume times molarity, okay? Okay, so we have, let's go back to our deal here. Up here now, we want to equate when we get the moles of base equaling the moles of acid down here, we're going to achieve pH 7, neutrality. And we're going to do that via the indicator. It's going to tell us that. So now we need to know what's the concentration of our unknown acid. On Monday, I'm going to be giving you vinegar. I'm going to say, what's the concentration of that vinegar? So you need to know a couple things. You need to know the concentration of the base up here. If we multiply the volume we use to achieve neutrality times the concentration of that base, we'll know how many moles of base we use. Down here, we're going to put a known volume of acid in there with a pipette. Okay. What we don't know is the molarity of the concentration of the acid. We're going to also use the VM again. So basically, we're going to have this equation every single time. We want moles of base. Okay, so at pH 7 or neutrality, that's what we end up achieving because our indicator told us that. So moles, remember over here, we can substitute oops. Okay, so we have moles equals the volume of the base times the concentration of the base equals the volume of the acid times the concentration of the acid. This is what we use now to figure out our concentration of acid. We solve for M. Okay, so we know the volume we put in of the unknown acid. We're going to use a volumetric pipette to do that. It'd be like 20 milliliters or whatever. Well, we don't know the concentration of the acid. From the burette, we know how many milliliters of base it took to neutralize the acid. That comes from the burette reading. We know the concentration of the base because we made it up. So now we just solve for concentration of the acid. So Nicole, do you have your hand up? Okay. All right, does this make sense? Kind of gone through 29 steps here. The bottom line is this relationship here. And you know what an acid is, you know what a base is. Concept of concentration is how many moles you have of that particular product in so many liters of solution, or usually it's water. So today we're just going to practice getting to the end point. Tomorrow you're actually going to calibrate. So there's practice, part A, part B. Practice today, part A tomorrow, part B Thursday. And then Monday, we're going to actually use vinegar, concentration of vinegar. Okay, does this make sense? Now, one thing about these guys, you have to make sure your units are compatible, because your burette's going to read in milliliters. What do you need to do with the milliliters? It has to be in liters. You need to convert it to liters. When you put the volume of acid in there, you're going to be using a pipette that reads in milliliters. What do you need to do? Convert it to liters, yeah. So everything needs to be in liters because that's what concentration is measured. Okay. So that's the theory behind titration. Now, titration is used outside of acids and bases too. For example, if you go get an allergy, I'm waiting for my allergist to schedule my testing on my arms. And what they do is it's called a titer, T-I-T-E-R, titer. And what they do is they titrate on your arm how much of the antigen it takes for a particular width of redness around the injection site. When it reaches that point, they know how much you're allergic to that specific antigen, called a titer. They use titration a lot in oxidation reduction reactions. For example, we're going to be doing a vitamin C lab. I think we're going to be doing a vitamin C lab, where we find how much vitamin C is in a particular food. Usually it's orange juice or something like that. And again, that's the oxidation reduction titration. And you have your bread again, you've got your unknown on the bottom, and then you titrate against the unknown. So it's a frequent used technique. Okay, so in your mind, VM equals VM. After all we went through today, that's what I want you to know for the titration labs. Okay. All right, that's what I wanted to cover today. So we have half an hour. Yeah.
Just make sure. So moles, like MOLES, is the same as are they different?
Yeah, I just abbreviated it. Yeah. So MOLE, not much of an abbreviation, but is equal to. The problem is the abbreviation for molecule is MOLC. And C looks like a little E if you're not careful. Like when we did a 602 times 10 to the 23rd, I'm usually I write MOLC, but I force myself to write molecules because it's too easy to think that's stands for mole. And that's a good abbreviation. The other one is hardly abbreviation at all. All right, well, why don't you guys look over your tests and make sure I did my arithmetic right.
Just a quick question. I wanted to know how to properly set up number of talents and like that.
Okay, wait a minute, let me.
Yeah, sure.